The image that stopped the world. On a quiet morning that felt ordinary in every possible way, humanity witnessed something extraordinary. After years of anticipation, delays, technical challenges, and global suspense, the telescope that had been called humanity's most ambitious eye in space delivered an image that did more than show distant galaxies. It reshaped perspective itself. The moment the first deep field from the James Webb Space Telescope was released, screens across the planet lit up. Scientists leaned forward in silence. Social media exploded, newsrooms scrambled, and for a brief moment, billions of people looked in the same direction, outward. The image wasn't just beautiful, it was profound. Where earlier telescopes had shown faint smudges of light, Webb revealed razor-sharp galaxies, some warped into luminous arcs by gravitational lensing, others shining like ancient lanterns from a time when the universe was still young. These weren't just dots, they were cities of stars, each containing billions, sometimes trillions, of suns. The image carried photons that had traveled for over 13 billion years before touching the gold-coated mirrors of Webb and finally landing on detectors colder than the darkest regions of space. To understand why this image matters, we have to go back decades. When the Hubble Space Telescope launched in 1990, it transformed astronomy. Its deep-field image in 1995 shocked the world by revealing thousands of galaxies in what appeared to be an empty patch of sky. That single exposure taught humanity a humbling lesson. The universe is far more crowded, and far more ancient, than we imagined. But Hubble had limits. It primarily observed visible and ultraviolet light. It could not fully pierce cosmic dust, nor could it see the most redshifted, ancient galaxies whose light had stretched into the infrared over billions of years. That's where Webb comes in. Unlike Hubble, Webb is an infrared observatory. Infrared light is crucial because as the universe expands, a discovery first confirmed by Edwin Hubble, distant galaxies move away from us. Their light stretches, shifting toward longer, redder wavelengths. The oldest galaxies don't just look faint, they look infrared. To see them clearly, you need a telescope built specifically for that purpose. Webb was designed with a 6.5-meter primary mirror made of 18 hexagonal segments, coated in gold to optimize infrared reflection. It orbits the Sun nearly 1.5 million kilometers from Earth at a gravitationally stable point known as L2, shielded by a 5-layer sunshield the size of a tennis court. The newly released image captured a region of space that, at first glance, appears small, about the size of a grain of sand held at arm's length. But within that tiny slice of sky are thousands of galaxies, each representing a different epoch in cosmic history. Some shine as they appeared just a few 100 million years after the Big Bang. That means we are not just looking far away. We are looking back in time. And this is what makes the image revolutionary. When Webb stared into that ancient region, it found galaxies that appear more mature and structured than many models predicted for such an early cosmic era. Some are surprisingly massive. Some show evidence of early star formation at rates that challenge existing simulations. For decades, cosmologists refined models describing how the first stars ignited and how galaxies gradually assembled. But now, Webb's data suggests that the early universe may have formed complex structures faster than expected. The implications ripple outward. If galaxies formed earlier and more efficiently, then perhaps our understanding of dark matter distribution needs refinement. Perhaps the initial density fluctuations in the early universe were slightly different from current estimates. Perhaps the physics of star formation in primordial gas clouds holds surprises we have yet to decode. But beyond equations and theoretical debates, there is something deeply emotional about this image. It connects us to a time before Earth existed, before the Sun was born, before our galaxy, the Milky Way, fully took shape. The photons captured by Webb began their journey when the universe was in its infancy, when hydrogen clouds were cooling, when gravity was sculpting the first cosmic architecture, when darkness was giving way to the first starlight. This era is often called cosmic dawn. For centuries, humanity could only speculate about it. Philosophers imagined eternal skies, early astronomers charted constellations, modern scientists developed radio telescopes and space observatories. But never before have we had such a direct, detailed glimpse into that primordial chapter. The engineering behind this success is almost as astonishing as the science. Webb had to unfold perfectly in space, a sequence of hundreds of deployment steps, each critical. A single failure could have ended the mission. The tension during those weeks after launch was intense. But when the mirror segments aligned and the instruments cooled to operating temperatures, the universe slowly came into focus. And now, with this image finally released, the wait feels worth it. What makes this moment historic is not just technological triumph, but collective achievement. Webb is an international collaboration led by NASA, with significant contributions from European Space Agency and Canadian Space Agency. Thousands of scientists, engineers, technicians, and visionaries contributed over decades. Generations dedicated careers to a telescope they might never personally see succeed. And yet, here it is, delivering images that redefine the limits of human sight. But this is only the beginning. Because this first image is not an endpoint. It is a doorway. Webb will analyze the atmospheres of distant exoplanets, searching for molecules like water vapor, methane, and carbon dioxide. It will peer into stellar nurseries hidden behind thick curtains of dust. It will observe supermassive black holes in the early universe, studying how they grew so quickly. And it will continue pushing back the timeline of observable cosmic history, inching closer to the Big Bang itself. Yet for now, we pause. We look. We feel small, and somehow larger at the same time. The image we have been waiting for does not just show us where we are in space. It reminds us that curiosity is one of humanity's most powerful forces. From cave paintings to rocket launches, from primitive lenses to segmented mirrors unfolding a million kilometers away, the journey has always been about seeing further. And today, we see further than ever before. But the deeper story of what this image truly reveals, about dark matter, early star factories, and the mysterious evolution of galaxies, is only just unfolding. When the long-awaited image from the James Webb Space Telescope was finally released, most people saw beauty. Astronomers saw data. Every speck of light, every curved arc, every faint red glow carried encoded information from a time when the universe was barely a few 100 million years old. The image was not just a photograph, it was a time capsule written in infrared light. The revolutionary power of the James Webb Space Telescope lies in its ability to read that light with extraordinary precision. Unlike ordinary cameras that capture visible wavelengths, Webb detects infrared radiation, light stretched by cosmic expansion itself. As the universe expands, galaxies move away from us. This phenomenon, first observed nearly a century ago, causes light waves to elongate, shifting them toward the red end of the spectrum. The farther a galaxy is, the more redshifted its light becomes. In simple terms, the deeper Webb looks, the older the universe appears. The newly released Deep Field image revealed galaxies so distant that their light began traveling toward us more than 13 billion years ago. That means we are seeing them as they were shortly after the Big Bang. But how do scientists know their age? How can they look at a faint red dot and determine how far back in time it belongs? The answer lies in spectroscopy. Webb does not just take images. It splits light into its component wavelengths, creating detailed spectra, cosmic fingerprints. Each chemical element leaves a distinct pattern of lines in a spectrum. Hydrogen, helium, oxygen, carbon, they all imprint signatures. By measuring how much these spectral lines have shifted toward the infrared, astronomers calculate redshift with remarkable accuracy. From redshift, they determine distance. From distance, they determine age. And this is where the surprises begin. Some galaxies in the image appear brighter and more structured than expected for such an early epoch. According to traditional cosmological models, the first galaxies should have been small, irregular, and gradually growing through mergers over time. Yet Webb is seeing galaxies that look surprisingly massive and mature far earlier than predicted. Spiral-like forms, rapid star formation, heavy elements present sooner than anticipated. This challenges assumptions about how quickly structure formed in the early universe. The dominant cosmological framework, known as lambda CDM, describes a universe shaped by dark energy and cold dark matter. Dark matter, though invisible, provides gravitational scaffolding for galaxy formation. After the Big Bang, tiny fluctuations in matter density slowly grew under gravity's pull. Gas accumulated, stars ignited, galaxies formed. But if galaxies assembled faster than expected, perhaps those early density fluctuations were stronger. Perhaps star formation in primordial gas clouds was more efficient. Or perhaps our simulations need refinement in ways we are only beginning to understand. The gravitational lensing visible in the image offers another layer of insight. Some galaxies appear stretched into luminous arcs. This effect occurs when massive foreground galaxy clusters bend spacetime itself, magnifying background objects behind them. It is a direct confirmation of Einstein's theory of general relativity, gravity warping the fabric of space. Through these natural cosmic lenses, Webb can observe galaxies that would otherwise be too faint to detect. In essence, the universe itself becomes part of the telescope. The cluster acting as a lens in this image amplifies distant light, allowing astronomers to probe deeper than ever before. Some of the faintest red objects in the frame may represent some of the earliest galaxies ever observed, perhaps formed just 300 to 400 million years after the Big Bang. If confirmed, these objects push us closer to understanding the era known as cosmic dawn, when the first stars ignited and reionized the universe. Reionization is another mystery encoded in the image. After the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. This created a cosmic fog that absorbed ultraviolet light. Eventually, the first stars formed and emitted powerful radiation that ionized the surrounding hydrogen, clearing the fog and making the universe transparent. By identifying early galaxies and measuring their light, Webb helps determine when and how quickly reionization occurred. Were early galaxies numerous enough to drive this transformation? Or were other sources, such as early black holes, also contributing? And then there are the stars themselves. Webb's infrared sensitivity allows it to peer through dense cosmic dust clouds where stars are born. Regions previously opaque now glow with hidden detail. In these stellar nurseries, gravity compresses gas until nuclear fusion ignites. Massive stars burn hot and fast, enriching their surroundings with heavier elements when they explode as supernovae. These elements seed future generations of stars and planets. The deep field image captures galaxies at different evolutionary stages, some forming stars at astonishing rates. By analyzing their spectra, astronomers measure metallicity, the abundance of elements heavier than hydrogen and helium. Surprisingly, some early galaxies show evidence of chemical enrichment sooner than models predicted. That suggests intense cycles of star birth and death occurring rapidly in the young universe. Then there are the black holes. At the centers of most galaxies lie supermassive black holes. Some in the early universe appear to have grown incredibly quickly, reaching millions or billions of solar masses in less than a billion years. How? Standard accretion models struggle to explain such rapid growth. Webb's observations may help identify early quasars, extremely luminous objects powered by matter falling into black holes, and refine our understanding of their formation. Each pixel in the image is layered with questions. Are we seeing the earliest generation of stars, the so-called population 3 stars, composed almost entirely of primordial hydrogen and helium? These first stars are thought to have been enormous and short-lived. Detecting their indirect signatures would be a monumental breakthrough. Are we observing galaxies that formed in isolation, or did they rapidly merge in chaotic environments? Are early galactic disks stable, or are we misinterpreting shapes distorted by gravitational lensing? The more Webb reveals, the more complex the cosmic story becomes. But perhaps the most profound realization is this: the universe matured astonishingly quickly. Within a few 100 million years, gravity had already sculpted vast systems of stars. The cosmic web, filaments of dark matter stretching across space, was already guiding galaxy formation. When the Hubble Space Telescope first delivered its deep field image, it hinted at this vastness. Webb now amplifies that vision with unprecedented clarity and depth. Where Hubble saw faint whispers of early galaxies, Webb sees structure. Where Hubble saw smudges, Webb sees detail. This does not mean previous models were wrong, but it does mean they were incomplete. Science advances through refinement. Each new instrument reveals layers previously hidden. Webb is not overturning physics, it is sharpening it. The data flowing back from its instruments will occupy researchers for decades. Papers are already being published, debates unfolding, simulations being rerun with updated parameters. And yet, despite the technical language and statistical models, the emotional impact remains. We are witnessing the universe becoming visible to itself. The atoms in our bodies were forged in ancient stars. The light captured in this image began traveling long before Earth existed. When those photons left their galaxies, there was no solar system, no oceans, no life. Now, after billions of years crossing expanding space, they end their journey on a mirror built by intelligent beings evolved from stardust. That connection is staggering. The image is not just about distance. It is about continuity. We are part of the same cosmic process that formed those galaxies. The same physical laws, shaping early stars govern the chemistry in our cells. The same gravity sculpting galaxy clusters holds our planet in orbit around the Sun. In the coming years, Webb will continue dissecting the faintest light ever detected. It will analyze exoplanet atmospheres, searching for biosignatures. It will trace the evolution of galaxies across cosmic time. It will help determine how common planetary systems like ours might be. But even now, with this single release, the boundaries of the observable universe feel closer and deeper than ever before. The image we waited for is not just a snapshot. It is evidence that humanity can build tools capable of reaching across billions of years. It is proof that curiosity, persistence, and collaboration can transform imagination into reality. And yet, perhaps the most astonishing revelation is still ahead. When the first long-awaited deep image from the James Webb Space Telescope was released, it did more than showcase distant galaxies. It marked a turning point in human awareness. For the first time, we weren't just imagining the universe's earliest chapters, we were directly observing them in extraordinary detail. The James Webb Space Telescope didn't simply take a picture. It extended the boundary of human perception almost to the beginning of time itself. And that changes everything. Because when you truly understand what you are looking at in that image, you realize something astonishing. Every tiny red arc, every faint galaxy cluster, every distorted streak of light is older than our planet. Some of that light began traveling toward us more than 13 billion years ago. At that time, the Earth did not exist. The Sun had not ignited. Even our galaxy, the Milky Way, was still forming from chaotic clouds of gas and dark matter. And yet now, billions of years later, that ancient light ends its journey on a precisely engineered golden mirror floating 1.5 million kilometers from Earth. That is not just science. That is poetry written in physics. For centuries, humanity's understanding of its place in the cosmos has been shrinking physically, but expanding intellectually. When Nicolaus Copernicus proposed that Earth orbits the Sun, he displaced us from the center of the universe. When astronomers discovered that our Sun is just one star among hundreds of billions, we became less central still. Then the Hubble Space Telescope revealed that our galaxy is just one among trillions. Each discovery reduced our physical importance. But something else grew in its place: our capacity to understand. The Webb image reinforces that paradox. Physically, we are tiny. The deep field shows thousands of galaxies in a region of sky no bigger than a grain of sand held at arm's length. Each of those galaxies may contain hundreds of billions of stars. Many likely host planets. Some may host oceans. Perhaps even life. Yet intellectually, we have never been larger. Because the same universe that formed those galaxies also formed us. The carbon in our cells was forged in ancient stars. The oxygen we breathe was created in stellar explosions. The iron in our blood once existed inside a dying star billions of years ago. We are not separate from the cosmos, we are made of it. And now, we are capable of studying it. That realization transforms the Webb image from a distant astronomical observation into something deeply personal. It is a mirror, not of our faces, but of our origins. But the impact of this image goes beyond philosophy. It reshapes science in real time. Webb's discoveries suggest that galaxies may have formed faster and grown larger earlier than many models predicted. Some early galaxies appear surprisingly structured. Some show evidence of intense star formation and chemical enrichment, only a few 100 million years after the Big Bang. That means the universe matured rapidly, faster than many simulations anticipated. If those findings continue to hold, cosmologists may need to refine aspects of the standard model of cosmology. Dark matter distribution, early star formation efficiency, and black hole growth rates are all under renewed scrutiny. And then there is the question that echoes louder than ever. Are we alone? Webb is not only looking deep into the past. It is analyzing the atmospheres of exoplanets orbiting distant stars. By studying how infrared light interacts with atmospheric gases, astronomers can detect water vapor, methane, carbon dioxide, and potentially even biosignature combinations that hint at life. Imagine the impact of detecting a chemical imbalance that strongly suggests biological activity. Even before such a discovery, the Webb image changes our perspective. It suggests that the building blocks of planets and potentially life existed very early in cosmic history. If galaxies were forming rapidly, if stars were exploding and seeding space with heavy elements sooner than expected, then rocky planets may have formed earlier too. Life elsewhere, if it exists, could be far older than life on Earth. Perhaps civilizations had a billion-year head start. Perhaps they rose and fell long before our planet cooled. Or perhaps the universe is still waiting for consciousness to bloom in many regions, just as it did here. Whatever the answer, the Webb image expands the stage on which that question is asked. There is another powerful dimension to this moment: unity. The James Webb Space Telescope is the result of collaboration between NASA, European Space Agency, and Canadian Space Agency. It represents decades of international effort. Engineers, scientists, programmers, mathematicians, technicians, thousands of individuals from different nations worked together to build something no single country could achieve alone. In a world often divided by politics and conflict, this telescope is a reminder of what cooperation can accomplish. When we look at the deep field image, we are not seeing borders. We are seeing shared curiosity. And perhaps that is its most important lesson. Throughout history, certain images have shifted humanity's self-image. The Earthrise photograph from lunar orbit showed our planet rising above the moon's horizon, fragile and alone. The pale blue dot image captured by Voyager revealed Earth as a tiny speck suspended in a sunbeam, inspiring reflection about unity and responsibility. The Webb deep field stands beside them. But this time, instead of showing us ourselves from far away, it shows us the ancient universe from which we came. It tells us that we are late arrivals in a vast, evolving cosmos. It tells us that stars lived and died long before our sun ignited. It tells us that galaxies assembled in complex structures while our future solar system was nothing but interstellar dust. And yet, despite arriving late, we arrived capable of understanding. That may be the most extraordinary fact of all. The universe produced complexity through gravity, nuclear fusion, and time. From simplicity emerged structure. From structure emerged chemistry. From chemistry emerged biology. From biology emerged intelligence. And now, intelligence studies the universe. The photons captured in that image traveled for billions of years. They crossed expanding space, passed through gravitational lenses, avoided absorption by interstellar dust, and finally struck a mirror engineered by conscious beings. In that meeting, between ancient light and modern mind, something remarkable happened. The universe became aware of its own history. The image we waited for is not an ending, it is a beginning. Webb will continue exploring stellar nurseries, mapping galactic evolution, probing exoplanet atmospheres, and refining our understanding of dark matter and dark energy. Future observatories will go even further. Each new discovery will raise deeper questions. But this moment, this first breathtaking glimpse, will always remain special. Because it was the moment humanity looked back more than 13 billion years and saw not darkness, but light. Ancient light, persistent light. Light that survived cosmic expansion to tell a story. And that story says this: you are made of stars. You are standing on a small world in a vast universe. You are not the center of everything, but you are capable of understanding it. That is the true power of the image we have all been waiting for.